Okay. You got y prime, y double prime minus y equals 2 e to the x over e to the x plus e to the negative x or minus. See over hyperbolic cosine or hyperbolic sine. Yeah, it's plus. And this, and I'm going to let you kind of think about why it's so. Move the camera up just a little. Is e to the x over hyperbolic cosine of x. I'm not sure that's helpful, which is useful observation. Maybe not even a useful observation, just an observation. Now, did all that come through? Because my video here was a little choppy.
I can see it all. Yeah.
Okay. Okay. Well, maybe I was just freezing or something. You never know. Okay. Anyhow, your homogeneous equation your solution set is e to the x, e to the negative x. Okay. Because clearly, if y equals e to the x, y double prime is e to the x, and you have e to the x minus e to the x equals 0. For e to the negative x, again, y double prime would still be e to the negative x. You get a negative on each derivative, and it would still match up and give you 0. And of course, you can always go through your characteristic equation, r squared minus 1 equals 0, r minus 1 times r plus 1 equals 0, et cetera. Then, what in the world are you going to do for the non-homogeneous equation? Okay. Now, actually, I don't say right off the hand what to do, so let's just explore it. Okay. Not worried about that 2 for the moment. E to the x over e to the x plus e to the negative x equals 1 over 1 plus e to the negative 2x. Okay. Now, what I don't see is any hint of an annihilator that would work on this. And I don't, right off the top of my head, have a clue. I have clues about what to do. I'm not sure they're going to work. I don't know what combination of derivatives I would use to try to match this up. Okay. So I'm going to explore a little bit. And I could either do this in this form, knowing the derivative of the hyperbolic cosine, hyperbolic sine, and using the Kosher rule. Or I could do it in this form, I could do it in this form. Okay. I would either do this or this. I wouldn't mess with this. So now let's just do this. It's worth exploring this possibility. It might be good for you to see it. Okay, by the quotient rule, this is going to be e to the x hyperbolic cosine of x minus e to the x hyperbolic sine of x over the square of the hyperbolic cosine of x. then that's going to be e to the x times the hyperbolic cosine minus the hyperbolic sine. The hyperbolic cosine minus the hyperbolic sine is going to be this is e to the x minus e to the negative x over 2, e to the x plus e to the negative x over 2. And when you subtract the e to the x's go away, the e to the negative x's coincide. So I think I'm getting e to the x times e to the negative x over hyperbolic cosine of x, which is the reciprocal of the square of the hyperbolic cosine of x. And it should be e to the negative x. But the reciprocal of the hyperbolic cosine of x, it's been a while since I did a lot with hyperbolic sines and hyperbolic cosines, so I don't have a lot of intuition at hand about how that derivative works, so I'm going to have to find out. Okay, so okay, reciprocal of hyperbolic cosine of x, derivative of, I could use the quotient rule, or I could write that as a hyperbolic cosine to the negative 2. I'll do this and treat it as a composite, and I'm going to get negative 2 times the hyperbolic cosine of x times the hyperbolic sine of x, and I hope I'm doing that right. And let's just check that out again. Composite, so the derivative of composite is going to be derivative of the inner function negative 2. And then times the first power times that. And I'll check that out. And then the hyperbolic cosine times the hyperbolic sine. Oh boy. Doing it in my head is, it's going to be e to the x plus e to the negative x times e to the x minus e to the negative x, which is going to be e to the 2x minus e to the negative 2x, which is pretty convenient. Then you got the factor of 2 in the denominator. I'm not sure I'm getting that negative 1/2 from. But this looks promising in a minute, and it kind of does. Yeah, I don't need the 2. I got the negative 1/2 times this. Unless I've done something stupid, this is then amenable to annihilation after 2 derivatives. Okay, I don't want to go too much further with this. I'll work this out and tell you a little bit more about it. It's a little tricky to find out what to do with a non-homogeneous equation. Looks like I've got an annihilator of the second derivative of this, so I could convert the function into a y fourth derivative minus a third derivative equals derivative of this and go from there. Now I've actually got a solution here, and the solution isn't all that compatible with that. So things I'm doing here, I'm trying to shortcut it, just trying to get some intuition. Take that process as just a hint as to how you might begin to approach this. There's probably something simpler, more elegant that I'm simply not seeing. And I could be making some mistakes in my derivatives here because I'm doing them in my head. And then, of course, I could go back to this form or this form. And what I get from this form doesn't look like it'll be all that compatible with what I think I'm getting here. And I'm still not seeing anything that I can annihilate. And I want to go to annihilators because I can't see a trial solution that would give me something of this form. Or this form. Or this form. Okay. But that's what I'm kind of looking at. Don't see it right off the top of my head. So I kind of apologize for that, but I'm stuck in this and don't want to take much more class time on it. So as I say, I need to write that one out and play around with it a little bit. Hopefully I'll see something. Okay, so bottom line, at least 3 of the problems on that set were over a section that I skipped and didn't notice that I'd skipped when I set up the course back in January. So apologize for any anxiety that caused you. I'll tell you just a little bit about Kosher Euler equations because they're kind of neat, but I'm not going to test you on them and you're not going to be responsible for them. But there's a lot you can see about these things just by analogy with what we've done. Kosher Euler equation, I'm just going to give you an example rather than give you the general form. Second order Kosher Euler equation would be like an x squared y double prime plus x y prime plus y equals something else. I'm just going to do a homogeneous equation here. Just to demonstrate the trial solution. The trial solution be y equals x to the m, where m is unknown. Okay. Can't remember you did a trial solution of that nature in solving the Bernoulli equation a while ago. Okay. And of course, if you had constant coefficients here, your trial solution would be an e to the RT. Okay, so just a different kind of trial solution. And the reason this trial solution works out nicely is when you take 2 derivatives and x to the m, you get x to the m minus 2. And multiply that by x squared, and you got x to the m again. And when you take 1 derivative of x to the m, you get x to the m minus 1, but you multiply that by x, and you get x to the m again. And this one already has x to the m, so everything's going to have an x to the m on it. So using that trial solution, you get x squared times, now what's your constant? First derivative is going to give you a factor of m, and function is going to become x to the m minus 1. Second derivative is going to give you a factor of x of m minus 1, x to the m minus 2. So you're going to end up with m times m minus 1, x to the m. And then you're going to have plus x times m x to the m minus 1, and this should be m minus 2 here. Multiply them out before I multiply them out. And then this would be plus x to the m equals 0. And now you can see that you got m times m minus 1 x to the m plus m x to the m plus 1 equals 0. Plus x to the m. Factoring things out before I factor them out. Okay. Factor out the x to the m or divide it through. You have then m times m minus 1 plus m plus 1 equals 0, which is m squared plus 1 equals 0. You're going to get an m squared here. You're going to get a minus m. And plus m takes care of it. You get this. So you get m equals plus or minus I. So that y1 equals x to the I, y2 equals x to the negative I. Now, at this stage, you get into natural logs and exponentials and Euler's identity and stuff. And since I'm not going to test you over, I'm just going to say, you can deal with this, okay? Just using the Euler identity and just the fact that well, you have things with the natural log and the exponential that I don't want to write out and explain. But they're pretty straightforward. If I had a negative y here, then I'd have m squared minus 1. And m would be plus or minus 1. So my solutions would be either x to the 1 or x to the minus 1. So your solution set would be the set x 1 over x. Okay. If I have a repeated root, well, then we have to deal with that. But there's a lot of analogy here between what you do with a Cauchy-Euler equation and what you do with just a second order equation with Koch coefficients. You get something much like a characteristic equation. You call it an auxiliary equation in this case. So this would be your auxiliary equation, but it's very analogous to characteristic equation. And that's how you solve some of the things that you didn't have a means to solve. Don't worry about it. Unless you're driven, don't go back and try to solve them. But if you do, we'll talk about them. Okay. So that's that. Now, the rest of what we want to talk about today is stuff that you're actually going to be pretty familiar with from the physics course you took spring before last. But it's been a couple of years since you had that course, so we'll spend a little bit of time setting things up. And I'll set these things up with the assumption that you remember, and that things will kind of refresh for you based on what you learned in that course. I'll set this board over a little bit. Let's get a better picture of it here. So your standard mass on a spring, and everything kind of runs together here, but I'm pretty sure you looked at a little bit of this earlier. I'm not absolutely sure about that. But we did first order equations with drag and stuff like that. And usually in this course, I've done that by this time. I should have reviewed. I think maybe we didn't do it. But anyhow, okay. Mass on a spring with no drag. We have an equilibrium position. Let's say it's right here. So here's your equilibrium position, where the spring force plus the gravitational force is 0. You have the position, we'll go to the center of the mass here. Okay, disregarding this more or less as a point mass then. Here's your position Y. And of course, then you're going to have a y-axis here with y equals 0 at the equilibrium position. At this position, the spring is more compressed, so it's pushing down. Let's say it's less stretched out. It's not pushing down as much as it was here. So that the net force is going to be downward, okay? And we're going to say, okay, with the position Y, F net at position Y is negative ky. Again, you can sort that out. Whatever the spring's doing, well, the spring here is pulling up harder than it is when the spring is here. So that the gravitational force, which hasn't changed, is a net, gives you a net downward force. So that the force here, and let's go ahead and use some color. Is like so. Well then, this gives us a differential equation. The net force is mass times acceleration, which is negative ky, because net force is just a mass. And of course, implicitly, we have a spring with force constant, K. I'm not going to review that. Your book will explain it if you don't remember, but I think you probably pretty much remember since we talked a lot about this. Okay, so you have mass acceleration is negative ky. Actually, you took the second semester physics. You had the first semester somewhere previously. I think it was maybe an AP course or something. So this might be a little fuzzier than I think it is. But your book should catch up on it. Acceleration is a second derivative position. Y is your position. So we get my double prime equals negative ky. So that your equation becomes y double prime equals negative k over m. Putting in a square root there because I'm skipping myself ahead. Negative k over m y. So what you have in the context of what we're doing here is y prime minus k over m y equals 0. letting y equal e to the RT, you get r squared minus k over m equals 0, and it's plus k over m minus here. Bring it over to the same side, you get a plus, and r then equals plus or minus square root of k over m times I. So that we do y1 equals e to the square root of k over 1, to square root of k over MIT. MIT is a good school. Okay, well, hard to get into. They waitlist everybody except people from good prep schools, pretty much. And they have their reasons for doing that. And also they look at special things people have done. If you haven't done anything outstanding, no matter how smart you are and how good your test scores are, pretty iffy about getting in there. Okay, well, that's digression on MIT and you know how my mind works. Okay, anyhow, very straightforward. Once you leave this, you get this, which is, well, I'm not even going to write it out. You know what to do there. You get e to the negative square root of k over m times IT. The solution set is a cosine square root of k over m t and the sine, and you can't read that, and there's some curly braces out here that don't even exist in my solution. But I'm just going to write this now as cosine of omega t sine of omega t omega equals square root of k over m. Interpretation. B cosine omega t plus C sine omega t, or A cosine of omega t plus 5 for reasons that I think we're familiar with based on what we did previously. Just using your trig identities, this could be put into this form where since B and C are arbitrary constants, A and 5 become your arbitrary constants. In this form, wish I had a better circle, but too low on the board. Your interpretation is, this is a circle of radius A. Here's a vector from the origin out to the circle, making angle phi. Yeah, that looks like it's opposite. I'll do one down here at some angle. If this angle is omega t, then right here is the vector whose x coordinate is cosine of omega t plus phi, which is circular model. As t moves on, omega t keeps increasing. Of course, it keeps wrapping around, and you keep going through the cycle where this vector goes around the circle again and again and again. The x coordinate, when the vector is here, the x coordinate is a. X equals a at this point. By the time the vector gets over here, the x coordinate is negative a. And it goes through all positions between here and here. And then when the vector comes back around here, the x coordinate is again a, and it goes through all positions, all x positions between here and there. Okay. And actually we're using y as the variable here. So you would actually model that in terms of the y-axis, but it's a straightforward model. So actually, since I'm using the cosine, I want to use x. Let me do this for y, because I think you've seen me do it for x a number of times. You've probably seen me do it for y as well. Since we're going to talk about y, and since that matches the picture here where you're moving up and down, it makes sense to do that. And my picture works better. Okay, so here is your y coordinate of the tip of this vector on the circular model. So y is a sine of omega t plus phi. I really need to draw you a better picture of that. Okay. Now again, you connect this form, it goes back to these solutions, to this form, just by simple trig identities for some two angles and so forth. Okay, what we get out of that pretty straightforward development is, yeah, this is the board I wanted to use. No reason we couldn't use cosine here. Your phi would just be different if you use the cosine. The omega is still going to be the same. So we have a circle. Let's try to draw a decent circle. Got a pretty good angle here. Not too bad. Actually, it came up pretty good. Now I'm probably going to screw up the center, but let's see. Okay. Now the way I drew this before, use some extra colors. So let's just say phi is this angle here. And the radius is a. And omega t brings us around to some position And omega t could be any number of revolutions that bring us around to the same position. The y coordinate of this point is y equals a sine of quantity omega t plus 5. And again, as t goes on, omega t increases. Okay. Let's say it increases linearly with t. Sine of omega t plus phi gives you the same result if omega t plus phi changes if omega t plus phi changes by 2 pi, 4 pi, etc. That is by n, well, I'm going to try this, 2n pi. So the period is two n pi over omega. Because if t changes by 2n pi over omega, omega t changes by 2n pi. Just multiply this by omega, you get 2n pi. And if t changes by 2n pi, if omega t changes by 2n pi, then omega t plus phi changes by 2n pi, giving you the same result. So that's the periodicity of your oscillation. Okay. So you go from any position, like this position here, and if t changes by any multiple of 2 pi over omega, means you're going to go from here down to here and maybe several times, but you're going to end up then back here. And it's something you really want to understand intuitively, because there's an analogy with circuits that we'll talk about in a few minutes. Okay, well, that's your basic model of harmonic motion, simple harmonic motion. If you have a drag force, well, that's the next thing we want to look at. Okay, so okay, what coefficient do I want to use for drag force? I pull it up on WebAssign, except it's probably kicked me out by now. Let's see. Yeah, it's still got me in here. Maybe. There we go. Just to be consistent with the book, a delta, a gamma, what is your brought me to the right sec. No, it didn't. Section 2. I'm not sure we're going to do section 2. That's deflection of a beam. Okay, damp motion. Oh, they want to use beta. Okay. Okay, if drag force is minus beta times your velocity, which in this case is minus beta times y prime, then your net force is negative ky minus beta y prime. So if the thing is at this position, moving upwards, your drag force is going to be negative because we let upwards be positive, then y prime would be positive and negative beta y prime would be negative. Now, if you're moving upward through some viscous fluid, say water or air, or some other source of drag, maybe dragging this along a surface with friction, although friction doesn't act like that, so you wouldn't do that. Of course, you wouldn't probably do that with your harmonic oscillator. Second friction's too complicated. Anyhow, if you're moving upward, then drag pushes you back this way. Okay, just try moving your hand upward through water. You feel the force pushing down on your hand. And if you're moving downward, then your drag is going to be upward. Your y prime would be negative. The negative multiple of y prime would be positive. Okay, so there's your net force. This implies the equation y double prime plus beta y prime plus ky equals, well, it equals your net force. Well, we're going to say it equals 0. Okay, we're going to say there are no other forces. So this is your net force. So y double prime will equal this, so that this sum equals 0. So y equals e to the RT implies r squared we do have mass in the denominator. It's mass times y double prime equals this, divide through by the mass. So that R equals, you can go to the quadratic formula. And you're going to get this. Now, there are various ways to simplify this. I want to factor out a beta over 2m. So I'll leave you to puzzle over the algebra because I think you're capable of it. Let's see if I'm capable of it, if I write this down correctly. Okay. That's going to give you 1 here and divide the square of this into this. Okay, divide the square of this into this means you're going to multiply by the reciprocal of the square of this, and it's going to give you a 4m squared make sure I've got no. Okay, little bonehead mistake there. It's the square root of b squared minus 4ac. Well, there's your minus 4ac. A is 1, c is k over m. But it's just beta over m that we're squaring, not beta over 2m. I have this beta over 2m here doing its best to distract me, and it succeeded. So it's going to be a beta over m. Now, wait a minute. Yeah, you've got the 2 in the denominator. So you've got a 1/2 here. So distraction aside, algebra, I'm glossing over a little bit more algebra than I really wanted to. But what you're going to do is you're going to factor out a beta over m here. The 2 here comes from the denominator of your quadratic formula. You can work it out, just write the thing out. But factoring out a beta over m here, we end up with the reciprocal of the beta over m squared, multiplying each of these, giving us 1 here. And then it's going to be minus 4 km over beta squared. Again, I multiply through here. It's like multiplying through by beta squared over m squared in here, which will give you back this. And the beta squared over m squared will give me, well, the betas will cancel out. And the m squared in the denominator will give us an m. So that's going to work. Okay. There are my 2 possible values of r. And of course, now this can be written as this. Okay. Now, a couple of things we can see about this. If four km over beta squared equals 1, then we have a square root of 0 here. And we just end up with 1 plus or minus 0. We end up with a repeated root. Okay, now how does that happen? Well, that means that 4 km over beta squared has to be just right. Okay, in other words, k and beta have to match up just right to make this 0. Now, if k is small compared to beta and m and all that stuff, meaning this term is small, then we get something, well, we get a real number under, we get a positive number under here, because if this is small, subtracting it from 1 still leaves us a positive number. So we get 2 real solutions. Now, if k is big or beta is small, then this term is going to be bigger than 1, and we're going to get 2 complex solutions, 2 complex valued solutions. And the two complex valued solutions are going to give us oscillatory behavior, but there's also going to be an exponential attenuation. Not sure how much of that I want to get into because I want to make the analogy with circuits. Because with circuits, you get exactly the same stuff, just with different symbols. Instead of beta, you got resistance. Okay. Instead of mass, you've got inductance. And instead of, where is it? Instead of K over M, you've got capacitance. Intuitively, again, if you've got a really stiff medium like molasses, then your beta is going to be pretty big. You try to move fast through molasses, you get a lot of resistant force. And unless you have a really stiff spring, you're not going to have a lot of success oscillating in molasses. Whereas if you have air, you have a very small beta, very small drag force. So unless you have a really wimpy spring, it's not going to have too much effect. In either case, well, I guess I better write out the solutions here. Okay, you have this, your solution for the plus. And this could be expressed as e to the negative beta over 2m times t times e to the square root of 1 minus 4km over beta t. That's written kind of small. I think if you just look at this, you understand what we get, and that's called beta squared. And if there's an algebra mistake in that, you can correct it. The concept is pretty clear. Give myself a little more room. So this and this. Okay, well, large case, small beta, and you could just take the original solution. If beta was 0, well, then you'd have a problem here. But as actually beta 0, you do have a problem, except that you got a 0 here, I mean a 1 here, and this is going to be a complex solution. And I want to interpret that with really low frequency. Okay. So I'm not going to worry about that. Anyhow, for large K and small beta, you're going to have something very close to the type of oscillation that you get with the circular model. For large K and small beta, then you get e to the negative beta over 2m t times a cosine of omega t plus phi okay, where omega is the square root of 1 minus 4km over beta. And something about that strikes me as wrong. Because your limit as beta goes to 0 would get all messed up. So I might have done something in my algebra here. Still, this is the type of solution you would get. E to the negative beta over 2m times t is going to be a decreasing exponential. And this is going to be oscillatory. Now, sometimes that oscillation will give you a negative, sometimes it'll give you a positive, so that your solution is going to run between these two curves. Something like this, a decreasing oscillation. So you're oscillating, but less and less each time. It's like you're following that circular model with a shrinking, an exponentially shrinking circle. Okay, analogy you might want to think about. That's a pretty good idea. Okay. If beta is large enough, this just becomes some real number, this or this, become real numbers. And you essentially just have this solution, this exponentially decreasing solution, modified slightly by what you get for the positive and the negative here. So you just get something that's very much like an exponential solution. You can read the details of that. Okay. I want to make the analogy with circuits now. With circuits, and we've talked about circuits, so. Total voltage drop around a loop is 0. Well, we have a loop here. And let's say we've got a resistor and an inductor and a capacitor. So we have a resistance, an inductance, and a capacitance. Okay. Let's say we're going around the circuit this way, and we have some current I. Then the voltage drops or R times I which is R times Q prime, where Q is the charge on the capacitor. Current changes because charge on the capacitor changes. At the rate at which charge on the capacitor changes is the rate at which charge flows around this loop, and that's your current. Then you have Q over C, charge on the capacitor divided by the capacitance. And then you have L times I prime, which equals L times Q double prime. Now, total voltage drop is 0. So Li prime plus Ri plus Q over C equals 0. Meaning, of course, then that L Q double prime plus R Q prime plus Q over C equals 0. Don't like that denominator, so I'm going to say LC times Q double prime plus RC times Q prime plus Q equals 0. And there are other ways to do this. You divide through by L, or Q double prime plus R over L Q prime plus Q over LC equals 0. We would generally use one of these two. In this form, the characteristic equation is R squared plus R over L and capital R resistance versus lowercase r. And then you have plus 1 over LC equals 0. So that R equals big R over L plus or minus the square root of big R squared over L squared minus 4 over LC, all divided by 2. And I chose to use this form because your coefficient of R squared would be 1, so the denominator is simpler. There are advantages to this form also. You want to work it through either way. So that's going to be R over 2L multiplied by I don't like the square. I'm going to get there, but I'm stuck with it. Now, every form has its advantages and disadvantages. And I do this, every time I do this, I do it in a different form. Got to multiply through here by L squared over R squared to factor out an R over L. And then I've got the 2 that goes along with that. So I'm going to have 1 minus for L over R squared C. Don't like that square in the R. Something doesn't seem right. Okay, but as before, R acts like your drag. Okay. If you have a resistance in a circuit, that dissipates energy, and there's basically a drag on the circuit. Okay. Your capacitance, the reciprocal of your capacitance, acts like your force constant. Okay. The bigger C, the more, the bigger C is, the more charge you're going to be able to hold in this thing. And the more slowly charge is going to dissipate, given all other factors being equal. Okay. L acts like mass. The more inductance you have, the greater the magnetic field you get when you change the current. Well, the greater the magnetic field you get, as a result of your current, and that magnetic field then tends to resist the change in current, just like mass resists the change in velocity. Okay. So you have analogies that your book, I think, will spell out, and I can talk more about. I love to talk about this stuff. If we look back here, it's a little harder to make the analogy here, but beta is like drag. Resistance is analogous to drag. Okay, your mass is like your reciprocal capacitance. I'm sorry, it's like your inductance. And your force constant is like your reciprocal capacitance. Okay. You get exactly the same kind of solutions depending on how big R and L and C are. So that you get oscillatory behavior. You have repeated solutions. Okay, oscillatory behavior, if this 4L over R squared C is big enough. Again, I don't like that constant, so make sure I have my algebra correct here. I probably want to put this in a different form because it doesn't feel right to me. But anyhow, yeah, you have that. So you can have oscillatory behavior with your exponential e to the R over 2L, and really you've got to be a little careful about that. It's negative R over 2L. So I'm going to put the negative out here. From this, you're going to get an e to the negative R over 2L times t, which is a decreasing exponential, which in the case where these numbers give you oscillatory behavior, gives you a circuit that does this. You charge up your capacitor, say, you close the switch, and your circuit oscillates. But the resistance taps off energy, so you get that decreasing exponential around your oscillatory behavior. If you don't have any resistance, then again, you got to be a little careful about how the zero here works with the zero here, and you want to put it in a little different form, maybe like so. But you just get oscillatory behavior. capacitor drives charge off of it because the capacitor plates repel each other. So you have charge that moves through here, but the faster it moves, the more resistance it gets from L. So eventually the capacitor is discharged. You have as much current flowing as possible. And then the current tries to charge up the capacitor, but you have this inductor resisting the rate at which that can happen, and results in your oscillatory behavior. I have to describe that. I need a little more time if I want to really describe how that works. We did that in physics. And hopefully with the generator and stuff like that. Unfortunately, we're able to feel the effect of C. We're not able to feel the effect of L because we don't have large enough inductors. Okay, well, there it is. That's your model. And the models here are models of oscillatory behavior of masses on springs, or pendulums, because pendulums act the same way, and RLC circuits. A lot more we could say. And your book does a few things, like you got two springs in parallel. You have to think about how that works. You don't have a whole lot of that, but that's pretty much what you have. Okay, so getting toward lunchtime. I'm running out of gas just a little bit, you can probably tell. But we're right on time. Any questions?
Not that I can think of.
Okay, well, I think you're going to enjoy the section. And I think maybe we're not going to do all of chapter 5, even though I've got assignments for all of chapter 5. I don't remember off the top of my head what the third section is. If this thing will even give it to me, yeah. You have nonlinear models. We haven't done enough with nonlinear higher order equations to really understand most of those models, but we might talk just a little bit about it. The second section is mostly deflections of a beam. So we'll make a decision about whether we actually look at that section much. You have a fairly simple equation. The physics of it is something that you probably haven't dealt much with. It's kind of a first semester topic that you usually don't address in the first semester of a calculus-based physics course because it requires the differential equations. So you have kind of an intuitive idea. It's like you got a cantilever beam, a beam that's set in concrete on this end, let's say, but free on this end, and you're jumping up and down on this end. What happens to the beam? Or you just have people sitting along the beam. How does it deflect? Kind of interesting stuff, but we're not going to be able to derive the equations. We just use them as boundary value equations. We might do a little bit with that. Now, we do need to do a midterm exam. Have you thought about when you might want to do that?
Well, this weekend would not be good because I'm heading out of town this weekend, but maybe either sometime next week or next weekend.
I was actually thinking along those same lines. It would be just on the first 4 chapters.
Okay.
And you're in pretty good shape with that. And since we're not going to do all of chapter 5, we're going to be able to relax a little bit on the pace of the assignments. Be able to spend at least one day maybe reviewing, or just give you one day where all you need to do is just review. And we can kind of play that by ear. But go ahead and do the section 1 of chapter 5 for Tuesday. And then maybe no further assignments for the week. Does that make sense?
Yeah, that sounds good.
Okay, that gives you plenty of time to prepare for the midterm. It doesn't give me too much time to get creative, which would be to your advantage. And we'll see how that goes. Okay, we'll talk about it Tuesday. Let's say tentatively next weekend.
Okay. Sounds good.
Okay, good. Well, I'll see you next time. Any questions?
I don't think so. See you Tuesday.
Some of that physics ring a bell.
Yeah, I'm sure once we get a little bit more into it, it'll probably continue to ring more bells. But I had a pretty intensive AP physics course, so and then obviously your second semester physics course. So I think I've got an okay handle on it.
Yeah, well, I think you probably do. At least enough that it'll come back to you. Like I say, it's been a couple of years and you probably haven't used it. But okay, very good. Well, I'll let you go first in case you have any other questions. Stick around and ask them, but leave when you're ready.
All right. I'll see you Tuesday.
Yep.